We are learning about exponents, and then next time we'll learn scientific notation, specifically, which is just kind of an application of exponents, a really neat application. We've touched on exponents a little bit whenever we were talking about prime factorization and kind of a more efficient way of writing things out. So we've definitely had some exposure to this already. There's going to be a number of exponent rules that we are going to have, properties, if you will. So exponent properties and rules. The product rule says when I multiply two things together, for instance, b to the m times b to the n. So in other words, both of these have the same base. They may have different powers, they might have the same power. I can bring them into a single exponent with that same base and just add their powers. Real quick, let's do a quick review of exponents, of some of the basic rules and laws behind exponents. So, for instance, you're going to have, this is the general form b to the n, b to the n, or b to the nth power. That's how we're going to read it. And what it tells us how many times we're multiplying the base to itself. B is the base, n is the exponent here. N tells us how many times we will multiply b to itself. And that's pretty much, at least when n is a whole number. That's at least our interpretation when n is a whole number. For instance, 2 to the fourth, that means I take my base of 2 and I multiply it to itself so that it shows up 4 total times. You could argue I'm only multiplying 3 times. 1, 2, 3. But when I say 4 times, I mean how many times does it show up? 1, 2, 3, 4. 4 times. That's how much I'm multiplying it to itself. That's the whole purpose of exponents. Exponents tells us how many times we're multiplying it to itself repeatedly. And so you can do it just piece by piece. Do 2 times 2, that's 4. Times 2 again, that's 8. Times 2 one more time, that's going to give you 16. Think about something like negative 3 to the 5th power. Notice the negative is in parentheses. So we're going to multiply negative 3 to itself so that it shows up 5 total times. Negative 3 times negative 3 times negative 3 times negative 3 times negative 3. Now notice, if I paired these negatives up, that'll become a positive number, whatever it'll be. I can pair these negatives up, that'll become a positive number, but there's one odd man out. And that's going to make the whole thing go negative. That's going to make the whole thing go negative. So we'll have negative. And then you just have to figure out what 3 times 3 times 3 times 3, blah, blah, blah is. That ends up being 243. Thus, this ends up being negative 243. So if I raise a negative number to an odd exponent, an odd number, 1, 3, 5, 7, 9, 11, 13, etc., it's going to end up with a negative number because there's going to be one odd man out that makes the whole thing negative. If I raise a positive number to any positive exponent, it's going to stay positive, so it doesn't matter. Now compare that to, what if I raise negative 3 to the 4th power also? That means that gets rid of the odd man out. I have negative 3 times negative 3, that'll become positive. Negative 3 times negative 3, that'll become positive. So the answer is going to be positive. In this case, it turns out to be 81. Positive 81. So we end up with a positive number. So if you take a negative number, but you raise it to an even power, 2, 4, 6, 8, 10, 12, etc., you're going to end up with a positive number. In fact, that fact is very important to the very structure of algebra, but we won't go into uber detail about that. Now let's look at some of the rules that we're going to find on the PowerPoint, but let's do them kind of our own way. The product rule says if I have some b to the n times b to the m, I can bring them into a single exponent, or a single instance, and add their exponents like that. For example, if you have 5 to the 4th power times 5 to the 3rd power, you can bring them into the same 5, add their exponents, and you end up with 5 to the 7th power. Now, we won't actually compute that because that'll be a really large number. But we can leave it as 5 to the 7th power. The real question we should be asking is, why does this rule make sense? That's a good question. Imagine you did have 5 to the 4th times 5 to the 3rd. Well, 5 to the 4th here, that's saying do 5 to itself 4 total times. And then 5 to the 3rd, you're saying do 5 to itself 3 total times. And then you're multiplying these together. So how many times do you see 5? Well, 4 of them from here, 3 of them from here. So you see it 7 total times. So that's the same as saying 5 to the 7th power. Now this is just an example. It doesn't prove the rule, but it kind of helps demonstrate it. And you can see why this product rule makes a little bit of sense. Let's look at our next rule, the power rule. And what the power rule says is that if you already have a number that's an exponent, you already have an exponential number like this, and you go the extra mile and raise it to an exponent, you can actually multiply their powers together. Of course, we want to see an example of this. So let's say you had 3 squared, and then you were going further, and you were raising that to the 5th power. So you have the number 3 squared, and then you're raising that to the 5th power. What the power rule says is we can multiply those exponents, not add them, multiply them, and you end up with 3 to the 10th power. Again, the question we should always be asking is, why does this make sense? Why in the world does this rule make any lick of sense? Well, we're taking 3 squared and we're raising it to the 5th power. In other words, we're doing 3 squared to itself 5 total times. 3 squared times 3 squared times 3 squared times 3 squared times 3 squared. Now that it's written like this, we can see that we're just taking the base of 3 and using the previous product rule, we're adding 2 up here 5 total times. Well, wait a minute, when you add 2 to itself 5 times, that's just saying you're multiplying it by 5. So we'll let that one sink in a little bit. The power rule. So we have a rule for when you multiply exponential quantities that have the same base. We have this power rule. Now we can talk about when you do division. And we could talk about the quotient rule. And actually, let's make it red. The quotient rule says that if I have my base to a power and I divide it by my base to another power, I can bring them into the same exponential house by subtracting the bottom power from the top power. So for example, if I had 7 to the 9th power, let's make it a little easier. 7 to the 6th power divided by 7 to the 4th power. that's going to be equal to 7, a single 7 to the 6 minus 4 power, or just 7 to the second power, 7 squared. Why, again, always, why does this make sense? Well, 7 to the 6th divided by 7 to the 4th, let's use a different color. 7 to the 6th on top there is going to be 7 times 7 times 7 times 7 times 7 times 7. 6 total times. On bottom, 7 to the 4th is going to be 7 times 7 times 7 times 7. And now notice you'll be crossing things out here. You can cross out these 7s, these 7s. In other words, you're deducting the total number of 7s there are on top based on how many there are on bottom. Thus, you're just left with 2 7s, 7 times 7, or 7 squared. So again, it's not a proof, it's just a demonstration of this rule. But it kind of clicks once you see what's going on, once you know that you can cross them out. Something like that. So getting back to the exponent rule, we have these rules here. The last rule we will look at is the exponent rule. If b is any real number other than 0, if I raise it to the 0th power, I get 1. So, I mean, that's anything. If I do 5 to the 0th power, that's a big fat stinking 1. Negative 17 to the 0th power, as long as I put the negative 17 in parentheses, that's 1. 3,426,856.214 to the 0th power, I'll make that a little better, is equal to 1. You raise to the power of 0, you get 1. With one exception. If I try to raise 0 to the 0th power, this is undefined. So your exponent base has to be a number other than 0, so that if I raise it to the 0th power, I get 1. So that's a pretty easy rule to remember. Here's just some more examples of that. 7 to the 0th is 1. Pi to the 0th, pi is the number 3.14159, dot, dot, dot. But you raise it to the 0th power, you get 1 all the same. Now, negative 5 here is in parentheses, and I'm raising it to the 0th power, that'll be 1. Down here, it's a little confusing. This is going to come out to be negative 1. And it's because the negative 5 is not in parentheses. What that means is order of operations tells us, I'll write this out because this is an important distinction. Here, the entire negative 5 is being raised to the 0th power. But down here, order of operations tells us that the 5 is being raised to the 0th. Then we're applying the negative to it. So down here it's saying, no, you have to do 5 to the 0th first, then you're just slapping a negative sign in front of it. That's why written like this, it comes out to -1. So don't let that totally throw you off. The next most important rule to remember is the negative exponent rule. If for some reason I have a negative exponent, b to the negative m, you can make it a positive exponent by changing it into the denominator of a fraction, and unless there's some other number here, you're going to have a 1 as the numerator. It's kind of a weird rule, but it actually works. A negative exponent, so think of it like this, a positive exponent, 3 to the 5th, tells me to multiply 3 to itself 5 total times. A negative exponent, though, 3 to the negative 5th, actually tells me to divide by 3 5 total times. A few examples. 8 to the negative 2nd power tells me to really do 1 over 8 to the positive 2nd power. So that's 1 over 8 times 8. That's going to be 1 over 64. So a negative power inherently puts things like in the denominator. Five to the negative third does something similar. That becomes 1 over 5 to the positive third. That's 1 over 5 times 5 times 5. 1 over 125. 7 to the negative 1st power tells me to do 1 over 7 to the 1st, but the 1st power just means do it to itself that many times. So it just stays 1 over 7. But because of the negative exponent, it becomes this fraction, 1 over 7. We will cover this powers of 10 next time. This is not something we want to cover. What I want to do now is I want to go into your actual homeworks and work some of the example problems with you. So powers of 10, that's related to scientific notation, which we're not doing just yet. We'll be doing that next week after your exam. So let me pull up. Let's see what's a good one to do. This is your product rule assignment. We'll just work a couple of these. Perfect. So here, let's see if I can make it a little larger. We have y times y to the 11th. It wants us to multiply the expression using the product rule. Now it uses a variable instead of a known exponential base, but that's okay. Y times y to the 11th. Remember, in this first case, this y, if it's not otherwise written, it's implied to have an exponent of 1. So that just becomes, according to the product rule, y to the 1 plus 11th power, or y to the 12th. To put in exponents, there's a couple things you can do. You can hit Y, and then if you hit Shift 6, you'll bring up the caret key. Or there is down here, you can just hit this. No, you need to put the Y in first. Then you hit that, and then you hit 12th power. So you have a couple of ways of putting exponents into this. Now this one looks bad. 5x cubed times 3x to the fifth. But now we're going to group our similar terms together. This 5 and this 3 are just numbers. This 3 and this 5 are exponents on the x. So what you can do is you can rearrange, thanks to the old commutative property. I'm going to rewrite this as, I'm going to put the 5 and the 3 together at the beginning. Then I'm going to do the x to the third and the x to the fifth at the end together. Now 5 times 3 is just 15. But x to the third times x to the fifth, I'm multiplying together two things that have the same base. So they're going to share that base of x, and I'm going to add their exponents together, 3 plus 5. And you're going to end up with 15x to the 8th power. Let's see. We'll work these together. This one looks daunting. Don't let it scare you. You've got a negative 6y to the 8th times a negative 4y to the 4th. First of all, you have a negative times a negative, so it's going to just become positive. And then you can drop the parentheses. It'll be 6y to the 8th times 4y to the 4th. And it'll be positive. Technically, you don't even have to write the positive sign. Now rearrange them, put the 6 and the 4 together, put the two y components together. 6 times 4 is 24. Y to the 8th times y to the 4th becomes y to the 8th plus 4, and thus you get 24y to the 12th. Like that. So it's not quite as horrible as it looks. Over here, group things together. You can drop the parentheses entirely here. Rearrange the similar terms together. 6 times 5, put those together. X to the 5th and x to the 4th, put those together. You can rearrange because everything's just being multiplied and you have that commutative property. Then arrange the y's together. Six times 5 is 30. X to the 5th times x to the 4th, they have the same base, then we'll just add their powers. So that becomes x to the 5 plus 4 power, y to the 2 plus 3 power, and that's all she wrote. Let's look at another one of these. Here's a good one. Oh my goodness, this is horrible. Look at this monstrosity. Oh wait, it's all to the 0th power. Don't let it throw you off. That's a monstrosity, but it's all to the 0th power. Now this one is a monstrosity. It didn't quite cover. That's okay. This one is a bit of a monstrosity, and it's to the 3rd power. So before we try to evaluate it, let's look at the inside first. You have negative 12, a to the 5th, b to the 6th, all over 6, a to the 8th, b to the negative 6th. You're going to look at it piece by piece. You're going to do the negative 12 divided by the 6th because those are similar. A to the 5th divided by a to the 8th. And then b to the 6th divided by b to the negative 6th. So first up, negative 12 divided by 6 is going to be negative 2. A to the 5th divided by a to the 8th, remember the quotient rule. You have a to the 5 minus 8th power. B to the 6th minus negative 6. So this becomes negative 2, a to the negative 3rd power, b to the 6 plus 6 power. And so this entire inside, before we raise it to the 3rd power, becomes negative 2, a to the 3rd, b to the 12th. And now we raise it to the 3rd power. What's going to happen is the 3rd power is going to apply to each of them individually. That negative 2 is going to get raised to the 3rd power. That a to the 3rd is going to get raised to the 3rd power. That b to the 12th is going to get raised to the 3rd power. And now we'll do each piece individually. Negative 2 to the 3rd, let's see, that's going to be negative 2 times negative 2 times negative 2. Oh, that's going to be negative 8. Now, a to the 3rd raised to the 3rd, remember we don't add these powers, we multiply them. So that's going to be a to the 9th because of the power rule. B to the 12th, then raised to the 3rd, we need to multiply these powers. That's going to be b to the 36th power. So ultimately, we're going to have negative 8, a to the 9th, b to the 36th. Oh, I didn't like it. Hold on. Use the quotient rule. Powers, products to power rule. Oh, I'm sorry. Did I forget something? Yeah, I made a mistake. That's my bad. I totally wrote it down wrong. This is, remember, this was a negative third power. I don't know why I dropped that here. So this becomes -3. That becomes -9. And then it wants your final answer to have positive exponents. So we're going to put a to the -9th on bottom. So I literally just forgot to put the negative sign, but we had it correctly originally. My mistake. There we go. A to the 9th. There we go. So yeah, I just forgot to put this negative sign here. My mistake. So that one was a pretty good problem to do. Let me see if I can find some nasty ones. Let's do some of the ones that are inherently trying to trick you or not. This is from just the homework that's called section 5.6 exponents. It says determine whether the following statement is true. 10 to the 24th divided by 10 to the 12th equals 10 to the second. You're tempted to say that's true, but that's not true. 10 to the 24th divided by 10 to the 12th, we do subtraction according to the quotient rule. That's not true at all. You're going to get 10 to the 24 minus 12, which is 10 to the 12. So that statement is false, but the statement 10 to the 24th over 10 to the 12th equals 10 to the 12th is true. So that one was just trying to trip you up a little bit. Let's see if there's any others like that. 2 to the 3rd times 2 to the 5th equals 4 to the 8th. No, you don't multiply the 2's together, yet you add their exponents and keep the same base. So this is going to actually become 2 to the 3 plus 5 power. And it's going to be 2 to the 8th, not 4 to the 8th. So the statement's false. The exponents are added. I guess that would be it. Yep. Let's see if we can find a nasty one here. This one's not nasty. It's -5 to the 0th. Notice the -5 is in parentheses totally. So it is just +1. Here, -2 to the 0th, -2 is not in parentheses. So we actually do 2 to the 0th first, which is 1, but then you slap the negative sign in front of it. So this one looks bad. Evaluate the given exponential expression. There's a couple ways we can handle this one. You can write 6 to the -5th times 6. First of all, that's 6 to the 1st. Then what you can do is you can add their exponents together because they have the same base. So that's going to be 6 to the -5th plus 1. -5 plus 1 is -4. So we end up with 6 to the negative fourth power, which according to the negative exponent rule, makes it 1 over 6 to the fourth. And it doesn't like that. Why doesn't it like that? I guess maybe it wants us to actually evaluate 6 to the fourth here. So we need to, so it's still 1 over 6 to the fourth, but we need to figure out what 6 to the fourth is to begin with. So it's good we're working this together so we can kind of see how it wants you to write things. So let's see. We're going to do this one without a calculator. 6 times 6 is 36. We know that from our basic multiplication table. Then we need to do 36 times 6. You get 216. So we still have one more we got to do. We got to do 216 times 6. And now all of them together, you get 1296. So 1 over 6 to the fourth is 1 over 1296. So it wants you to actually evaluate that, it looks like. So we weren't wrong, it just wanted us to go the extra step, the extra mile on that one. There we go. So these are all fairly interesting. We'll do this one as the last one. X to the fourth times x to the fifth to the negative second power. We can immediately turn that into that fraction. Well, there's a couple things we could have done. And now it has a positive 2 power. We can do it that way. Now we have x to the fourth times x to the fifth. Notice those have the same base. So we can put them into the same exponent by adding their powers. And we get x to the ninth. And then remember, it was still to the second power. So then I multiply the 9 and a 2 to get to the 18th power. So we've got the product rule and we have the power rule, and we have to know when to differentiate. When to differentiate between them. So this exponent business might actually be a bit challenging. I think if you take it step by step, it won't be so bad. So I would start working on this exponent homework right away. It's not due till Thursday, but I would get on it right now. And then what I would suggest to y'all, you can work on all the homeworks that are open right now. You can also work on any past due homework. Specifically, the homework that was due on the 11th is going to be covered on the exam. If you are in MyLabs Plus and you click on the grade book in MyLabs Plus, excuse me, you should be able to access homework assignments you've already worked on, and you can rework the problems. You can't improve your grade, but you can rework the problems for extra practice. So what I would do is today, I would rework some of the old problems from now the closed homework for extra practice. I would work some of the problems in the current homework involving exponents and things like that, linear inequalities, graphs of them. And I would come tomorrow armed with some questions you have for me, because we are going to spend tomorrow reviewing for exam 3, which is on Thursday. So tomorrow is Wednesday. We're going to review. Thursday the 18th, you're going to have your third exam. So I would work on this stuff and bring in some questions you have, and I'll work them during the review time. I'll also, if nobody has questions, I'll just work some problems here and there over the material that is covered. Remember, the exam 3 here is going to cover all of the homeworks. So it's going to cover material from the homeworks that were due on February 11th. So that's linear graphing, graphing linear functions, graphing linear equations using slope and y-intercept, writing equations of lines. It's also going to cover the material for homework that's due Thursday night, the 18th. Linear inequalities, simplifying irrational numbers, and then all this business with exponents, product rule, quotient rule, power rule, etc. So just keep in mind, if you need that in writing, you can click on announcements in Canvas. You can see the exam 3 announcement, and you can see in writing what is all going to be covered. So keep that in mind as we have our exam this week. Don't go anywhere. Let me take attendance. Brenda, Colby, Colton is in here. Guthrie, Hannah, Lily Ruiz, Micah, Madison Perry, Priya is in here. Riley, Sheridan, Cheyenne. Okay, that should do it for today. Guys, please stay warm. If you have to drive anywhere, be very safe.